Hello, in today's class we are going to look at a topic called supercapacitors, and this is a form of energy storage device that people work on and speak about in more recent times, and there are specific applications where this is the kind of device that makes a lot of sense, and in some places it may not be a device that can be used separately. Many times it may be used to augment a battery, so to speak. So, it is an interesting kind of device. So, we will go over it, and there is a lot of research that goes on in it, and a lot of applications that people are increasingly finding for it. So, in fact, if you look at the popular literature, if you read general articles on energy and so on, you will see a few different terms that are being used. You will see a term of supercapacitor. You also see this term electric double layer capacitor, and you also see this term ultra capacitor. So, these are the terms over and above just a capacitor. So, capacitor is something that is different, but I mean in some sense this is these three terms that you see here. So, this is EDLC, something like that. So, supercapacitors, electric double layer capacitor, ultra capacitor, they all refer to the same thing. Okay. So, this is what you will see in the literature, but this is basically what it is, that they are essentially the same. So, we will call it supercapacitor for the course of this class, and then we will I mean this is just something that you have to keep in your mind. So, our learning objectives for today's class are of course to first understand what is a supercapacitor, what is it that is since you are already aware of a term called capacitor, what is a supercapacitor, what is different about it, I mean why should it be even considered as something as separate from a capacitor, so to speak. So, how does it differ from a capacitor, and what are the applications it is typically suited for, what kind of applications it gets used for, and what are typical materials used for the supercapacitor. So, these are some of the learning objectives for our class, and within this context of these learning objectives we will look at the content of the class. So, a supercapacitor is nothing but a capacitor that has very high capacitance. So, I mean you can make from different manufacturers you can get capacitors of different capacitance, but just because something has slightly higher capacitance does not make it a supercapacitor. We will see that you are looking at several orders of magnitude difference in capacitance. So, see when a capacitor is simply two parallel plates, two metal plates, right, and there is some dielectric material in the middle, could even be air, but you typically have some dielectric material. So, you charge this up as supply, you attach this to some battery and you charge it up. So, you will get positive charges here and you get negative charges here, and correspondingly you will get the opposite charges here lining up with this positive charge. You will get negative charges from the dielectric, you will get positive charges here. So, this is how it stores up the charge in the capacitor, and then you can later release it, and then you can get the charge back to you. So, the charge that is usually there is given by CV, where V is the voltage you applied and C is the capacitance, and this is charge. So, this is voltage in volts, capacitance in farads, and charge in coulombs. So, this is what you will get. Okay. So, this is the relationship. So, we are talking of capacitors where the capacitance value is very high. So, therefore, for the same voltage you get very high amount of charge that is being held there. So, this is something that we look at. It has high energy density, generally relative to other options that you have. The voltage that it can give you is a little low, cycle life is very high. We will talk about this as we go through the other option, I mean details of the supercapacitor. Generally cycle life is high, high in the sense we are looking at again several orders of magnitude. That is the point that you have to remember. As we look at numbers, you will see it is not just high by a relative sense of a factor of 20% or 30% or even 100%. We are looking at difference both in capacitance, in cycle life, etc., of several orders of magnitude, so to speak. Basically it charges as well as discharges much faster than batteries. So, that is the key that you have to understand, that it charges and discharges much faster than batteries, and therefore, there are applications where the battery where the change in circumstance is kind of fast and you want something to store that energy quickly. So, there a battery will not be able to do the job. Although a battery can store energy, it needs some time to pick up that energy. But supposing you are delivering that energy so fast that you do not have that time, you have only a few seconds during which you have delivered a whole amount of energy and you want the battery to hold it, the battery is unable to pick it up. Supercapacitors are in a very good position to pick it up. So, that is why the supercapacitor is interesting. So, in a sense it bridges the gap between regular capacitors and rechargeable batteries. Okay. So, this what I have shown you here is a typical regular capacitor. So, we will see that some more again anyway, but this is a regular capacitor. So, this is not what we are doing here, we are talking about supercapacitor, and the supercapacitor bridges the gap between these kinds of regular capacitors and rechargeable batteries, where you have an anode, a cathode and an electrolyte. So, you will have, so this is a regular capacitor, the rechargeable battery will have anode, electrolyte and cathode. Okay, so, this is how we have the rechargeable battery, and then you go again you charge it, discharge it, etc. So, between these two is where the supercapacitors end up coming. So, we will look at that. So, some for example, I just mentioned to you that it is ideally suited for conditions where the circumstance is changing fast and you need the energy to be handled rather quickly. So, for example, if you look at regenerative braking. Okay, so, regenerative braking is the braking that is these days being done in electric vehicles. In fact, you could do it in any other vehicle also, but generally since the electric vehicle is set up to run everything operationally using electricity, the scheme of any energy that is any energy transaction that is happening, people try to convert that to electricity. So, normally in a regular car you press the brakes just become hot. Okay, so, they become very hot, and essentially that is what they are doing, they are converting your kinetic energy into heat and releasing it. So, there is a lot of friction that is put there, it converts the kinetic energy of the car into heat and then throws it out into the atmosphere. So, that is really what is going on. So, that is why when you are going on hilly terrain and you are climbing up and climbing down and so on, your brakes can heat up very extensively if you are continuously using the brakes. So, that is why they keep telling you use a gear, lower gear, and enable the gear to help you slow down your vehicle rather than just keep on pressing your brake. You have to press the brake if you need it, but basically this is what is happening. So, when you keep pressing the brake continuously in a say 1 hour downhill drive, that really heats up the brake to the point that they may fail. So, you have to be careful with your brakes, but that is what is happening in a conventional vehicle. In a conventional car, that is exactly what is happening. Now, in electric cars, the idea that when you try to generate electricity back from something that is moving, it slows down whatever is moving. So, you are using that energy that is there in the rotational process to generate electricity back, just the way a dynamo would work in a cycle that you had, except that there also the dynamo is pressing to slow down the cycle, but you do not want it to slow down the cycle. Here you are consciously using this electricity generation process to brake the car, to enable braking for the car. Okay, so that comes to a halt. So, regenerative braking, as you can imagine, is something that is happening in fractions of seconds, right. So, fractions of seconds to a second is what you see traffic, you are driving in traffic, you need to hit the brake, you hit the brake immediately, you do not hit the brake over several minutes, you hit the brake instantaneously. So, the braking process occurs over a fraction of a second. So, that is what I meant by saying that the time scale is very small. In that time scale, in that fraction of a second, the entire energy that was there in the car, the kinetic, let us say the car was travelling at say 30 kilometers an hour. Okay, and half a second later, not even half a second, maybe 0.2 seconds later, you have the car at 0 kilometers an hour. Okay, so, whatever was the weight of the car, so if you look at half mv square, this much kinetic energy was available. So, if a car is about, so this is half into let us say 1000 kilogram car, so 1000 kgs you have, and V is 30 kilometers an hour. So, that is we have what we have 3000 no 30,000 meters in, so you will have 30,000 in 60 minutes. So, you basically have this goes 500. So, you have 500 meters per second per minute and you divide this by 60. So, you will have whatever 50 by 6 meters per second. So, that is the speed. So, roughly about what is it 8.3 meters per second, that is the velocity it is travelling at. So, you have half into 1000 into 8.3 square. So, this is the amount of energy that the car has in joules. So, that is quite significant. So, this is about 64, so about 30, 35. So, you are looking at 35,000, about 35,000 joules. Okay, so 35,000 joules you have. So, this is 64 by 2 is about a little more than 64. So, I am just assuming say 70 divided by 2 is about 35, and 35 into 1000 is 35,000. So, you have 35,000 joules of energy in a car that is travelling at 30 kilometers an hour. It travels about 8 meters every second, and you are essentially in 0.2 seconds you are bringing it to a complete halt. So, in 0.2 seconds this much energy has to be stored somewhere. A battery will not be able to pick up this much, even though there is maybe a battery pack inside, it will not be able to. Generally it takes time, it takes a lot of time for all the reactions to happen, for the electricity to be picked up by the battery. So, a battery typically is unable to pick up 35,000 joules in 0.2 seconds. Okay. So, you need something else which can pick up this 35,000 joules in 0.2 seconds if you want to really do regenerative braking. So, that is the kind of quick transition that which a battery cannot handle, that a supercapacitor handles. Okay. So, that is the point that we want to understand. So, that is one application. Similarly, loading and unloading. So, you load something on some loading process of adding a weight to something and then removing the weight from something. So, you need suddenly a fair amount of energy to lift something up, put it somewhere and then release, right. So, again you need a huge amount of energy being delivered shortly in a short duration of time. You have to pick this object up, everything is sitting quiet, suddenly you pick up this object which could be 500 kilograms, 1000 kilograms, whatever, pick it up, put it up into some shelf. So, this may be happening in some storage warehouse or something. So, that kind of a thing where you have a machine which goes and does this, it goes and picks up a package, lifts it off the ground, puts it into a shelf, releases, comes down. So, that has to suddenly give you that energy in a matter of a fraction of a second. Again, that is something that a supercapacitor can deliver to you. Also, we spoke about regenerative braking, and that comes to the stop part of an electric vehicle. Similarly, start part of the electric vehicle also. Suddenly you want to start the car, right. So, in fact, if you look at what all people are doing to optimize the energy usage for a vehicle, which is a major aspect associated with running clean energy, environmentally friendly energy and so on, usage of energy. Right now they are implementing and the operational characteristic of a car in such a way that when you come to a halt for any reason, even let us say traffic is halted and you just come to a halt because the vehicle in front of you is halted, you just stop your car. At that instant it will switch off the engine automatically, you do not have to do any such thing. So, for example, in Indian conditions we are often told that if you come to a traffic light and you see that it is going to take some time, you switch off the engine, and that way you can save a lot of energy, because a massive amount of energy is wasted just waiting for the traffic light to change, traffic signal to change, right. So, most of the time we are advised to switch off the car, and many of us sometimes we do it, sometimes we do not do it and so on. So, a lot of energy is wasted. So, the modern day electric vehicles actually do it automatically. So, the moment it senses that the velocity is 0, it instantaneously switches off the engine, okay. It is completely, it goes to sleep for several seconds. The moment you start, it will immediately start. That is the beauty of it. You do not have to give it any, you do not have to give it even a second to start, almost instantaneously it will start. For it to almost instantaneously start, again that much amount of energy has to be delivered suddenly, all of a sudden you have to deliver this massive amount of energy to get this maybe 1 ton or 1.5 ton car to start moving again almost immediately. So, that is again done by the supercapacitor. So, both starting as well as stopping when you stop, picking up the energy in a fraction of a second is done by a supercapacitor. When you start, again delivering of a lot of energy in a fraction of a second is done by a supercapacitor. So, like this you can think of a variety of interesting end uses where the supercapacitor is quite unique in its ability to handle that task. So, the battery can take care of the general operation, okay, the general operation of the device can be handled by the battery. But the transitions, when you go from one operating point to a distinctly different operating point, could be from start to an accelerated starting point, or from an accelerated, I mean high velocity to sudden stop, those kinds of transitions which are drastic transitions occurring over a very short period of time. That is where the supercapacitor really makes a difference, which the battery cannot do. So, it is a good combination to have some set of supercapacitors and some set of batteries which are appropriately matched for a particular end use, so that the user experience, as a user you buy a vehicle and you use it, your user experience is very enjoyable. You do not see problems, you do not go back and complain saying that, you know, I used to drive a petrol powered vehicle, now I got this electric vehicle, every time I try to start it, it struggles for a fraction of a second and then starts, or a lot of energy is getting wasted, I am not seeing enough benefit from it and so on. So, all those things are not there, you will get all those benefits by having this combination, right. So, that is what a supercapacitor is capable of doing. Okay, so, we have three terms here, we have a supercapacitor, we have a battery and we have a capacitor. So, we will spend a little bit of time trying to understand what is the difference between these three. So, primarily if you look at battery, we know that it is an electrochemical device. Okay. So, the energy that is stored there is stored in the form of chemical energy. So, chemical energy meaning you have a reactant sitting on one electrode and another reactant sitting in another electrode. So, a chemical reaction happens, it is an electrochemical reaction, sure. So, there is a charge transfer between electrolyte phase and the electrode phase. In the end there is a chemical change that has happened to some constituent, right. So, some compound has formed. So, we saw lead could become lead sulphate, or lead oxide could become lead sulphate, cobalt oxide could become lithium cobalt oxide. So, many chemistries we saw for batteries. So, but bottom line being there is a chemical change, and that chemical change caused due to this electrochemical reaction is the manner in which the energy is stored. So, in a way you are storing it in the form of chemical energy. The energy that is being stored is being stored in the form of chemical energy, right. And to do this process you are using ions. So, you have, so for example, in a battery you will have let me just put it here. So, you will have, as we just saw, anode, cathode, and this is the electrolyte, and you have some ions going across, right. So, that is the process by which the activity happens. So, there is a chemical energy that is stored here. So, chemical energy is stored here, chemical energy is stored here in the form of whatever reactants are present, and then the ions move across and enable the process to happen. So, ions are moving and chemical energy is being stored. So, this is the idea with respect to a battery. Now, with respect to a capacitor, we are actually storing electrical energy. So, meaning you have a flat plate, another flat plate, and then in the middle you have a dielectric. Okay. So, you store electrical energy. So, where, as I said, you have all these charges here, you have minus charges here, you have plus plus plus, minus minus minus. So, you do not have ions, you have electrons basically, and the energy is being stored in in the form of electrical energy. There is no chemical change that is happening, we will discuss that some more, but there is no chemical change that is happening. The supercapacitor uses this aspect of it, that there is no, that it is electrical energy that is being stored, that is the aspect that in which it resembles a capacitor, but it uses ions, and in this process it resembles a battery. So, it picks these two concepts. So, that is what you have here, it uses ions and it stores electrical energy. Okay. So, you have similar thing, you have some electrode structure, something in the middle and another electrode structure, and then you have ions here. Okay. And that is how the supercapacitor is functioning. So, we will see that functioning a little bit in more detail in just a moment, but this is how the three of them differ. So, The supercapacitor uses ions just the way battery does, and it stores electrical energy just the way capacitor does. Okay, so this is the idea. So as I said, if you look at a capacitor, this is how a capacitor, a schematic of a capacitor would look. You would have two parallel plates, so one plate here and one plate here, which would be your electrodes, to which you connect an external battery. So you connect this to a battery. So this is the positive, and then I connect it here, negative comes here. Okay. So then in the middle you have a dielectric material, which is what which is shown here, and then as you supply electrons to this side and you take away electrons from here, what happens is this becomes positively charged, this becomes negatively charged. And then correspondingly the dielectric material, the side of the dielectric material that faces the negative electrode becomes positively charged, and the side of the dielectric material that is facing the positive electrode becomes negatively charged. So overall there is charge neutrality, there is just the same amount of positive charge as there is negative charge, etc. So you have charge neutrality, and also you should remember that this charge that you see here in the dielectric material is more or less in one region, it is a flat region. So you are looking at flat regions here. So in a very flat region you have a negative charge collecting on the surface of the electrode. Similarly a flat region here, both the electrodes are flat smooth surfaces. Here you again you have positive charge that is being collected. In the middle you have the dielectric material. There also on the surface of the dielectric material, on one side you have positive charge, on the other side you have negative charge. So this is the way in which the capacitor is functioning, okay, and in this process charge is stored, energy is stored, you can release the energy depending on your requirement. Now if you now look at a supercapacitor, some of these ideas are being carried over, but there is a lot of change. So that is what we are trying to understand here. So this is a supercapacitor. So again you can see here that there is something like an electrode, but here the electrode simply serves as a current collector. Okay, so this is like a current collector, and so this side also you have a current collector. Okay, and important difference that you have here is you have a porous electrode. On both sides you have a porous electrode, and we will talk about that in just a moment. In the middle you have a separator. Okay, so you have something called a separator, and then in this entire region that you see here, this entire region that you see here from here to here, you have electrolyte, this electrolyte. Okay. So this is what we are looking at in the context of a supercapacitor. So the point being that the current collector essentially enables electrical contact for the external circuit with these particles. In this case it is particles, but okay, we can look at other options available, but this is basically particles. So we have a structure where you have lot of particles that are present, and therefore because it is particles and not a solid object like this, this is not a, this is a solid flat object. Okay, solid flat surface, because it is a solid flat object. Here you have particles, so you have very high surface area that is divided and distributed. Okay, so you have very high surface area that is now distributed through the electrode. So it is not a flat surface, it is not a single flat location where the charge is present. We will talk about the charge, but anyway these particles are present, and there is an electrolyte that is present. That electrolyte is present over the entire extent of this region that I just marked here, between this current collector and that current collector you have electrolyte. So, this electrolyte actually penetrates into these particles. So, all these gaps that you see here, all the gaps that you see here are all filled by the electrolyte everywhere. Okay. So, all the gaps that you see here, so even here whatever gaps you see between the particles are all filled by the electrolyte. So, the electrolyte permeates into these into this porous structure. So, it is important that the electrode actually be a porous structure the way we have shown here in a schematic, but the specific purpose of it being a porous structure is to ensure that this electrolyte that we are talking about has penetrated into that structure and it is present throughout that structure. So, now whereas previously you just had this flat surface, so therefore, whatever was the geometric area was the area of the electrode. So, if it is a 2 centimeter by 2 centimeter electrode, that is a 4 centimeter square electrode, right. So, if it is 2 into 2, so that is 4 centimeter square electrode. Here even if your current collector is 2 into 2, that is only the current collector area only is 4 centimeter square, right. Actual surface area of the electrode is the surface area of each of these particles. So, you have to calculate the surface area of each of these particles, and the total surface area that you get by totaling up the surface area of all those particles is the surface area of the electrode. So, therefore, this has an extremely high surface area, very high surface area relative to this regular capacitor. The supercapacitor relative to the regular capacitor, the supercapacitor has a dramatically different amount of surface area. You are looking at several orders of magnitude higher surface area relative to the regular capacitor, and we are utilizing that surface area by enabling this electrolyte to penetrate throughout it. And of course, you do not want the positive electrode to directly come in contact with the negative electrode, right. So, otherwise you will short circuit the thing. If that short circuit, the concept of a short circuit is the same here also. So, you do not want a short circuit between the positive electrode and the negative electrode. That is why we have this separator material. So, the separator material will be sitting in the middle. It is a non-conducting material. It is basically also soaked in the electrolyte, so that the electrolyte is continuously present throughout the structure, and separator materials are essentially the same kind of separator materials that you would use even in a battery. So, you have these separator materials which are non-conducting, maybe polymer based materials which are porous. So, it is a porous structure, so you can have electrolyte going in all directions through that structure, and it fills that whole structure. So, those are the things you have done. You have put in a separator material which was not there in the capacitor, you have put in a porous electrode structure not there in a regular capacitor, and this electrolyte is distributing itself throughout this porous structure. Okay. So, this is the way in which the structure of a supercapacitor differs from that of a regular capacitor. So, as you can see, at least at a structural level and keeping in mind that there is so much more surface area, there is a huge difference between what a capacitor is, and what a supercapacitor is. Okay. So, this is the point we have to remember. So, now I will also point out that when you put an electrode in contact with an electrolyte, so this is electrode, and this is electrolyte. Okay, and let us say I connect this to the positive of a battery. Okay. So, when you do that, let us say, so you get a bunch of positive charges here. Okay. So, that part is still the same. Now, the electrolyte contains ions. Okay. So, the ions actually have they will have, so let us say I have negatively charged ions. So, those ions are now affected by the presence of this charge that is there on the electrode. So, naturally just the way you would expect in all these circumstances, the opposite ion gets attracted to this electrode. So, what happens though is that it does not necessarily just form a single layer here. Okay. Initial models used to suggest that it will also form a single layer, but because it is an electrolyte and because there is thermal energy associated with it, and there is movement of the electrolyte simply because of thermal energy that is present there, etc., it does not form a single layer, it actually distributes itself some more. So, much deeper into the electrolyte also you will have this region that is affected by the electrode. Okay. So, this is how the electrode electrolyte interface operates. So, we even here there is the notion of a double layer capacitor here, but the second part of the layer is not necessarily a flat structure, it is a little bit more distributed structure, that is the point we have to keep in mind. And you should remember that, you should also notice that on this side you have electrons and on this side you have ions. So, on one side of the electrode electrolyte interface, on the electrode side you have electrons, on the electrolyte side you have ions. Okay. So, when you look at this structure of the supercapacitor, what is different here relative to what I have drawn here is that the in the electrode, in this case I have drawn as a flat surface, whereas in a supercapacitor we have one flat surface which acts as a current collector, and just for to make for clarity's sake I will just only draw say 2 or 3 particles. So, I have a large particle, I have a small particle, and I have one more large particle, something like this, right. So, then the charges, so you put a positive charge here. This positive charge, because these particles are electronically conducting, is also the positive charge that distributes itself here. Okay. Then the negative charge gets distributed in this intermediate area is all containing electrolyte. So, all here you have electrolyte all over this place. So, you have negative charges collecting here. Okay. So, this is how now you have sort of extended the electrode into the system, you have extended the electrode into a larger region as opposed to a flat. So, what was 2 dimensional has suddenly become a 3 dimensional structure, right. So, that is what you have done. So, this is 2 dimensional, this is 3 dimensional. So, the electrode electrolyte interface is 3 dimensional, it is distributed into a larger region, and that is how electrical contact has been made here, the electrical contact is there, electrical contact is here, electrical contact between these particles is there, and that is how the positive charge that you put on the electrode goes to all of those particles, and then the electrolyte is has permeated everywhere, and that is very important. If the so, for example, if the electrolyte were not here, so supposing this region there is no electrolyte, then in that place there is no charge, this charge will not this charging will not happen, right. So, it is very important that the electrolyte penetrate everywhere. Once it penetrates everywhere you can do this, and of course you like I said this separator is also very critical, because the separator is not there, then you will have a short circuit across this, which is also not something that you want, you definitely do not want that kind of a situation. Okay. So, that is how the supercapacitor suddenly creates a situation where you are having a much higher surface area, and because you have much higher surface area and the charging process so fundamentally depends on that surface area that the amount of charge it holds goes up in a big way. So, if you compare this is the kind of plot that you would often see where they are comparing different kinds of power sources available to you, different kinds of energy sources available to you. So, if on your x axis we have specific power, okay, in watts per kilogram, so that is specific power, and on the y axis we have specific energy, watt hours per kilogram, so or joules per kilogram. So, if you see in comparison between batteries, supercapacitors and capacitors, batteries which usually will have a lot of charge that they can hold, but are relatively lower amounts of current that you can draw, will have high amount of energy. Okay. So, they are up on this axis, so they are up on this axis high amount of energy, but they are unable to deliver this at very high currents. So, they are actually low on the power axis, so they are on this side of the power axis. So, you go up vertically and move towards the I mean closer to the y axis, that is where the battery is set. So, this is the general direction in which the battery will go. The capacitors on the other hand go the other way. So, if capacitors are in this direction, they do not have much they do not have ability to hold a whole lot of charge, because it is just a surface just a little bit of charge held on the surface, but that whatever is there on that surface it can release really fast. So, therefore, in terms of power, which basically relates some voltage, but significantly depends on the current that you can deliver, it can deliver a high amount of current for a fraction of a second. So, that is a capacitor. The supercapacitor is somewhere in the middle. It has a little better specific energy than the capacitor, but it also has a little better specific power than a battery. So, it nicely bridges the gap between a capacitor and a battery in its ability to deliver power as well as hold energy, and in this process it can enable supporting both a capacitor and a battery in specific applications where each one of them can individually perhaps not do it. So, that is the way you may want to look at it. So, for example, if you look at charge discharge duration required for charge and discharge, if you look at capacitors, they typically require anywhere from milliseconds to microseconds to charge or discharge. Okay. So, milliseconds to microseconds is all it takes to charge or discharge a capacitor, and so that is a very tiny amount of time, and it is able to do the job that quickly. Batteries on the other hand take hours to charge and discharge. We are quite familiar with that, because all our mobile phones operate that way. Even though many of us may not have used an electric car, it is still not that common. Electric cars typically take several hours to charge. We usually, in fact, the normal operating scheme for an electric vehicle is that you bring it home, you leave it on charge overnight, and then when you leave it on charge overnight, next day you can drive for maybe 150 kilometers or 200 kilometers, something, some range will be there, 100 kilometers, 150 kilometers, something. That range happens the next day, but overnight you need to charge. So, you are charging for some 8 hours, 10 hours, etc. Mobile phones also, of course, these days they have faster charges and whatnot, but still you are looking at off the order of hours to charge a mobile phone completely. The supercapacitors on the other hand are again in the middle. As opposed to milliseconds to microseconds to charge, it takes several seconds to minutes to charge, and it also just requires several seconds and minutes to discharge. So, whatever energy it stored, it takes up that energy over the space of a few minutes, and then it can deliver it back in few minutes. So, from few seconds to a few minutes it will deliver that energy back. So, what it is doing in terms of time is significantly better than what the battery does. The battery requires several hours to do its delivery of charge or discharge. This is doing it in seconds or minutes, but it is holding much better charge than a capacitor. Okay. So, capacitor clearly is doing several orders of magnitude better than a battery in terms of time, but because it does not hold much charge, there is not a whole lot you can do with it, even though it gives you that whatever it holds, it gives you in a microsecond, but it gives you such a tiny amount in microsecond that you cannot really do a whole lot with it. You have to put a huge number of capacitors to even run something for a couple of minutes. So, that is not going to help you. So, this gives you a nice mix of the timing, which is just seconds to minutes, but the charge is distinctly higher than that of a capacitor. So, for example, also in the same context, in terms of cycle life, if you look at cycle life, you can see that capacitors are almost infinite in their cycle life. You can keep on cycling a capacitor for all practical purposes, nothing will happen to it, because you are really not doing any significant change to the material. It just remains whatever it is. So, nothing much is happening to it. So, it works for millions of several millions of cycles it will run. Essentially it is infinite for our practical applications. Batteries on the other hand, good batteries, I am not even talking of ordinary batteries, good batteries will probably give you about 1000 cycles. So, what is the real reason for this restriction? Well, a number of reasons are there. Usually what has happened, because there is a lot of chemical reaction that is going on, electrochemical reaction that is going on across the interface, and a few different things happen. For one thing, for example, at lithium ion batteries, for example, you will have an eventual degradation of the electrolyte, that may happen. But more importantly, the electrode itself is changing from one phase to another phase. You are having some reaction that occurs. So, some chemical that is there in the electrode changes to some other chemical. So, there is a change in one reactant becomes some product, and so in terms of a phase, one phase becomes another phase. Each phase has a different specific gravity, and so its volume will be different. So, invariably if you look at battery electrodes, their dimensions, even though you do not see it externally, you are seeing the same battery that is there, internally the dimensions of those electrodes could be changing. They could be swelling, they could be getting compressed, etc. So, there is a lot of structural change that happens at that level. It is not something that is visible to us, but at the level of those particles there is a lot of structural change that is happening. At the crystal structure level there is a lot of change that is happening. So, that puts a lot of stress at that size scale. So, many of those particles that are present in that electrode can break, can deform, or particularly if they break off they may lose contact with the rest of the electrode. So, you have an electrode and you have some two particles there, one particle here and another particle here. So, this particle, the second particle may at some other particle may break away from the electrode, and so now this is no longer in contact. So, if it is no longer in contact, it is no longer in a position to participate in the reaction. Okay. So, all these things happen in a battery. So, because there is swelling, there is a change in dimensions of the particles, etc., a lot of damage happens to the electrode over a period of time. Okay. So, it happens over a period of time. So, normally that is the reason why by the time you have done say 1000 cycles, the battery does not behave that well, it does not behave that particularly well, and then eventually you give up on it, get yourself a new set of batteries. On the other hand, supercapacitors are only charging on the surface. There is nothing, there is no chemical reaction that is happening. So, there is no species, chemical species in the form of ions. No ions are entering the electrode structure. I mean, in the sense, if you go back here and look at these particles, if I take an individual particle here, the ions just come to the surface. So, for example, if I say, so this is, let us say it is positively charged here, the ions come to the surface. But these ions are not entering the particle, they are holding position just around the surface, they do not enter the particle. So, in the particle nothing is happening, the particle does not swell, does not contract, nothing happens, it just stays more or less intact. So, therefore, in many ways it is undisturbed by the cycling process, and therefore, if you go down here, it is also in a position to give you a million cycles. A million cycles is a lot, I mean in the context of electric vehicles and so on. So, million cycles works out very well, because even though if you are doing let us say a battery that is running the electric vehicle is charged once overnight. So, you do one full charge and then the next day you run for 150 kilometers and you do a full discharge. So, if you used a battery for a 24-hour period of a electric vehicle, you do one charge and one discharge. But if the braking is a regenerative braking, which is using the supercapacitors, and you also let us say you take the assistance of supercapacitors to help in the acceleration and deceleration and so on of the vehicle, then especially in conditions where there is high traffic and heavy traffic and so on, let us say typical Indian conditions where there is a lot of start of the car, stop of the car, you have to slow down the car, accelerate the car and so on. In the same 24-hour period, you may have, I mean, several thousand, several hundred to a few thousand charge, discharge, acceleration, deceleration events. Right. So, you have several hundred to a thousand, maybe a few thousand acceleration, deceleration events. So, charge discharge of the battery happens only once, but the acceleration deceleration of the vehicle happens several hundred times, maybe 1000 times it happens. So, therefore, it makes sense that you use some device which can handle, I mean you really will utilize this, the fact that it can be cycled a million times is really useful to you, and the fact that the battery can be cycled only 1000 times is still okay for you. So, 1000 times if you can charge and discharge a battery, that already means 1000 days you can use the battery. Okay, so that means that is over 3 years, right, something like around 3 years you can run the battery, but a million times you are charging and discharge ability to run this 3 orders of magnitude more becomes necessary, because you may in fact use it a few hundred times each day. So, you will have to multiply it by a few hundred, and then that the million really works out comfortably for you, right. So, that is how these two taken together are really useful for electric vehicle applications, the battery supercapacitor combination. So, let us look briefly at the materials used for this supercapacitor, As I said, in general the idea is that there is no reaction as such happening on the electrode, it is just a highly porous structure which can interact very well with the with good electronic conductivity, which can interact well with the electrolyte. So, the electrode electrolyte combination is typically critical. Usually people are using things like activated carbon, carbon nanotubes and graphene. These are the kinds of materials that people are actively researching and working on. So, activated carbon for example is simply natural carbons that you get from let us say sawdust or some waste material from the agricultural sector, and then or you can take polymers, artificially derived polymers, and then you heat treat this in an inert atmosphere. So, you remove all the other species from it, you will get carbon. That carbon is typically called activated carbon, it has high surface area. So, that is what is this activated carbon. Then you have graphene. Graphene is like this, it is a single layer of hexagonally bonded carbon atom. So, this has very high surface area because you just have a single layer of atoms and you have high surface area. So, if you put lot of graphene particles together, you have a lot of very high surface area with which the electrolyte can interact. But the only issue is that the graphite is actually much more stable kind of a structure. So, if you give it enough chance, the graphene will realign and form restack and start forming graphite. So, you have to keep that in mind. So, you have to do something to stabilize it, so to speak. Then of course, there are carbon nanotubes which are cylindrical in structure. So, they essentially look something like that, a long cylinder with an end cap this side and an end cap that side, and in this you have all those hexagonally bonded carbon atoms, right. So, this is how you have the structure. So, you have hexagons like that, and then you get the so these hexagons are there all over the surface. So, this continues in all directions, and this is how you get this structure. You get cylindrical structures based on how you generate this the nanotube. You can get it straight the way I have drawn it, or you may even get highly curved coiled tubes like that. Okay, so, you will have some extremely coiled tubes also you can form. So, usually the CVD based synthesis of chemical vapor deposition based synthesis of carbon nanotubes, which is the typical kind of carbon nanotube you get when you commercially buy it. When you go to some internet site where they sell carbon nanotubes and you purchase it, mostly they are providing you chemical vapor deposition synthesized carbon nanotubes that will give you extremely coiled structure. If you look under an electron microscope, you will see the structures that look extremely coiled, whereas if you do arc discharge based carbon nanotubes or CNTs as they are called, then you get these straight structures. So, these straight structures or the coiled structures you can use in an electrode. So, for example, if this were your current collector, you could line all of these up on top of that. So, I have just drawn some for example. So, if you look at it charge wise, let us say this is positively charged. So, all of this will get positive charge, all the surface of this will get positive charge, and correspondingly you will get negative charge in all the negative charge ions will come around it. So, like this you will get, right. So, you get all this negatively charged ions which are collecting in the gaps between these carbon nanotubes, because you have the charge that has been built on the carbon nanotube and the positive charge is sitting in the carbon nanotube. So, this way you now have a very 3-dimensional structure over which you have a lot of charge that has been held together. Okay. So, this is how you take a flat structure and generate a lot more charge and store it in this structure. So, in terms of electrolytes, so that is the main thing, the electrode. The electrolytes are usually of 3 kinds: aqueous electrolytes, organic electrolytes or ionic liquids. Generally aqueous electrolyte means water is, I mean by using the term aqueous we mean water is present. If water is present it breaks down at 1.23 volts into hydrogen and oxygen. So it means if you are using an aqueous electrolyte, the voltage of that capacitor cannot be more than about 1 volt. So if you go more than 1 volt you are increasing the chance that the electrolyte will break down, so voltage gets restricted. Therefore, actually the more commonly used electrolytes are these organic electrolytes. Almost half of what is out there consists of in terms of a product is organic electrolyte based structures. They have lower conductivity, they usually propylene carbonate is the solvent used and some salt is used there, lower conductivity, but still it gives you some better stability under some circumstances, so that is used. More recently people have been really looking at researching these things called ionic liquids, where you are taking an organic salt and you are not putting any solvent in it. Okay, if you put a solvent you have to do a lot of purification of the solvent and so on to remove any moisture present, etc. Here you put no solvent, except that you pick an organic salt which has a melting point that is less than 100 degrees C, so that you can just keep the capacitor at that temperature and you will have a liquid electrolyte, but the liquid electrolyte is basically a molten salt. So that is how we operate this material, the supercapacitor. So the electrodes used are carbon based, either activated carbon or graphene or carbon nanotubes, and the electrolyte used is either an aqueous electrolyte or an organic electrolyte or an ionic liquid. So this is basically what is used. So that is our discussion on supercapacitors, both how, what is special about it, how is it different from a capacitor, how it differs from a battery, and what are the applications it can be used for, what are its capabilities, and what are some materials that are used to create this supercapacitor. So in conclusion, supercapacitors bridge the gap between capacitors and batteries. So they actually offer you a new realm of operation which neither the battery could offer nor the capacitor could offer. So it gives you a good mix of the positive aspects of both the battery and the capacitor. It is typically based on high surface area carbon being used as electrodes, with the charge being distributed into ions in the electrolyte. Okay, so the ions in the electrolyte distribute the charge and hold the charge, and that is how the electron ion combination helps you hold the charge. And typically you have aqueous, organic as well as ionic liquids which are being considered as electrolytes for supercapacitor. So that is our summary for of supercapacitors, and it is an interesting topic, has a very niche application in specific technologies such as electric vehicles, and is something that you will keep hearing about more and more. Thank you.